So we're going to be looking at the difference between exponential models and linear models. So whenever you're looking at exponential versus linear, let's just put the parent function for all lines, right? Y equals x. So if you don't, let's put y equals x. And for an exponential problem, we're just going to put y equals 2 to the power of x. So you can see the difference between an exponential model and a linear model. You can clearly see that's a curve and that's a line. Okay, so if we look at the tables, you can see the difference. You'll notice all these are going up by ones every single time. If I type in a 3, you got a 3. I type in a 4, you got a 4. Type in a 5, it goes up by 1. You can see it as it's plotting it. But if you look at an exponential model, you'll see that it's doubling. It's not going up by 2, it's actually doubling. So if I plug in a 3, you get an 8. If I plug in a 4, you get a 16. Plug in a 5, you get a 32. Plug in a 6, you get a 64. Why is that the case? Because these numbers are not going up at a constant rate. They are doubling. That's an exponential model, and that's why it looks like this versus like this. So let's take a look at some of these situations here. Okay? It says every year 39 million cars cross the Golden Gate Bridge. Every single year. So after 1 year, 39. All right. So it starts with 0, 0, then 139. Then after the second year, it's going to go up to 78, but it's only going up by 39 million every single year. So this is going to produce what's called a line because it's going up at a constant rate of 39 every single year. It says the number of visitors to the Eiffel Tower in Paris increases by 1.5% each year. So let's just imagine there were 10,000 people and it increased by 1.5%. What does that mean? What is 1.5% as a decimal? Okay, it's 0.015. Some of you may have been taught to move the decimal over to places like that. But an easy way is just to take whatever your percentage is and divide it by 100%, and that will give you your decimal every single time. Now, if I'm increasing by 1.5%, that means I'm starting with 100% and I'm increasing it by 1.5%. So that technically means I'm at 101.5%. So our model would be like this. This would be your growth rate because it's growing. That's your A value, that's your B value. And you're probably, what's the A value, what's the B value? In an exponential model, your A value is your initial amount, and your B value is either what's called your growth or your decay factor. It's either growth or decay. If B is greater than 1, we call that growth. If B is less than 1 but greater than 0, we call that decay. All right, so we got a growth factor and we have a decay factor. So I'm going to show you guys what it means to increase by 1.5%. So if I start out with 10,000 visitors and I increase it by 1.5%, then the next year they'd have this amount. And then the next year they would have this amount. And then the next year they'd have, you'll notice these are not going up at the same rate every single time. So if you wanted to figure out like what would be the amount of visitors after say 20 years, you could put 1.015 and just raise that to the power of 20, and in 20 years, boom, it's up to 13,460. Obviously, there's going to be more visitors to the Eiffel Tower than that. I was just using that as an example. All this being said, it's not going up in a linear fashion. It's going up in an exponential way. Okay. So here we go. Here we have a table. These are all going up by 2's. That looks like that goes up by 7. Then that goes up by 10. And then that goes up by 15. And then that goes up by 21. And then that goes up by 30. All right. Yeah. So if I look at all this, I'm like, these are not going up at a constant rate. It's not the same rate every single time. It goes 7, 10, 15, 21, 30. That's not linear, that's exponential. Okay. And last but not least, you'll notice these are all going up by 2's. Okay. This one goes up by 6.9. If I take 44.1 minus 36.9, 44.1 minus 36.9, I get 7.2. And if I do 51.1 minus 44.1, I get 7. 57.9 minus 51.1, 6.8. So I have enough information to let you guys know this is going to be more modeled as a linear function versus an exponential, because even though these aren't the same number every single time, what are they relatively close to? They're relatively close all to the number 7. So the table represents the cost of buying a small piece of land and a remote village since 1990. The thing that best models this relationship would be a linear function, not an exponential. You'll look at the last one and you can clearly see I'm going to choose exponential because they're not all close to the same number. They are increasing quite a bit. The gaps are increasing. Here, the gaps are staying relatively close to each other. So that's why we'll choose linear. Okay. So right now, we're going to take a look at 4 more problems. Exponential expressions in word problems. And this is where it's going to be very useful to have your equation, y equals a times b to the power of x. Remember, a is always your initial, and b is always your growth, or it could be a decay factor. B is greater than 1, we call that growth. If the b value is less than 1 but greater than 0, we call that decay. A manufacturer plant earned $80 per a man-hour of labor when it opened. Okay. Each year, the plant earns an additional 6% per man-hour. So it's starting off with 80. And each year, it's earning an additional 6%. So in order to get the growth rate, you're at 100%, you got to add 6%, which is 106%. So my decimal is 1.06. And we're doing it after 3 years. I could raise that to the power of 3. Okay, I could raise that to the power of 3. So which one models this? 1, 2, 3 being multiplied together, and there's my initial value. So it's going to be answer choice C. I could rewrite this as 80 times 1.06 raised to the power of 3. Just remember, 106% as a decimal is 1.06. All you have to do is just divide it by 100%, and that gives you the decimal. Shota invests 1,000. That's the initial value. It is multiplied by 1.02 each year. Okay. After 5 years of growth, that's going to be my answer. So 1 plus 1.02 to the power of 5, there's the 1,000. It's going to be answer choice A. Oh, whoa, no, it's not. That's not going to be answer choice A. It's supposed to be 1 plus that. It's answer choice C. Whew, that was a close one. If that was a 0.02, then that would have worked out. Okay? But that matches right there. All right, Benjamin invests 400 in a savings account. That's your A value. It earns 5% interest each year. After 3 years, it's going to be 1.05 to the power of 3. So 1.05, 1.05, 1.05. That means right there, that's to the power of 3. So I'm choosing answer choice B. And last, Javier bought a painting for 150 and it increases by a factor of 1.15. So it increases by 1.15. What's the value going to be after 7 years? That's what I'm looking for. So it starts there. There's the 1.15. There's the power of 7. That's going to be my answer. That's how easy it is. Just remember, the formula you're going to need is right here. Okay? And it looks like all of these were growth. So being that they're all growth, it makes it pretty easy. That's it.